Okay, so today with Roberto Valandro, tell us about 5D Higgs branches from simple flops and quasi-homogeneous cDV threefolds. Take it away.
Thank you very much, Julius, and thank you very much for the invitation to talk in the Quiver meeting. I'm very happy. Today we'll talk about a series of work that I did in collaboration with Andres Cornucci, that is in the audience, and with my two bright students, Mario De Marco and Andres and Giovanni, that, by the way, are applying soon. So this work is in the context of understanding 5D n=1 SCFT from the paradigm of M-theory on non-compact, singular Calabi-Yau threefolds. For this, there is a nice dictionary between the geometric data and the 5D theory data. For example, the Higgs branch is governed by complex structure deformations of the singularity, while the Coulomb branch by the resolution. Depending if it is small resolution, large resolution, you have the Coulomb branch or what is called the extended Coulomb branch. So this is known since these are old facts, let's say, but there are much more to say about this relation, as we will see in this talk. Now, what we did was to develop a method that allowed us to approach two issues. On one side, by studying some simple theories, we were able to construct a mathematically interesting class of threefolds with a simple flop, and computing with a novel method their Gopakumar-Vafa invariant that I will call GV in the rest of the talk. On the other hand, we could be able to classify the Higgs branches of an infinite class of 5D theories that correspond to an infinite class of Calabi-Yaus that are classified and are called quasi-homogeneous compound Duval threefold isolated singularities that are relevant for example, for CFTs coming from type 2B compactified on the same threefolds. Maybe I can say also something about this later. So in particular, the threefold that we are interested in are non-compact Calabi-Yau threefolds that have a fibration structure of this form. So basically they have a fiber that is a surface, and the base of the fibration is just a complex plane parameterized by a complex coordinate that we will call W for the rest of the talk. What is this surface? The surface is the deformation of an ADE singularity. Now, for those that don't know what is an ADE singularity, this is a point-like singularity in a surface, and it's called ADE because these singularities are in one-to-one correspondence with ADE Lie algebras. And how this, roughly speaking, this correspondence work? Well, blowing up these surface singularities, you get a bunch of spheres that intersect in the same pattern as the linking diagram of the corresponding ADE Lie algebra. For example, if you have E6, you just read this part of the equation. This is an equation for an E6 singularity. If you resolve this singularity, you get 6 spheres that intersect in this way, and you can see immediately the correspondence with the linking diagram. In particular, the intersection form of these spheres is equal to minus the Cartan matrix of the ADE algebra. Now, this S is not generically, on a generic point of the base, is not this surface, this singular surface, but it's a deformation of it. So it's a smooth surface that is a deformation. The deformation is just obtained by adding some monomials to the equation, to the hypersurface equation, getting a smooth surface. Now, if you let the coefficient in front of this deformation to depend on W, then what you get a vibration of this sort, in which at the generic W, this mu are different from 0, and you get a S that is a deformation of an ADE singularity, while requiring that this mu are equal to 0 at the origin, you have that at the origin, the surface has the ADE singularity. Okay? The class of threefold that we are interested in are such that that X is a point-like singularity at Y equals 0, at the origin of this family, precisely at X, Y, and Z equal to 0, where the singularity of the surface also leaves. Okay, so in principle, having a one fiber that is singular doesn't mean that the full family is singular, but we will actually study classes of threefold that are singular. Okay. Now, these are not strange threefolds. The simplest case is the conifold that most of us know very well. The conifold is defined by an hypersurface in C4 of this form. It's singular, it's a point-like singularity at the origin. And there is if you resolve this singularity, this is a small resolution because it blows up just as two spheres, so P1, at the point where there was a singularity. Now, if you put M theory on X, you get a quite trivial theory. You get an hypermultiplet charged under a flavor U1, so a global U1 symmetry. This hypermultiplet comes from M2 branes wrapping this rigid P1, vanishing P1, while the U1 you understand because it is related to a background vector multiplet that comes from the tree form in M theory. Okay, so in which sense this is the conifold is a fibration of a deformed AD singularity? Well, if you look at the equation and you set W equal to 0, you see that what remains is the equation of C2 mod Z2, that is the A1 singularity. Okay, this A1 singularity, remember the A1 is as just one node, the Dinkin diagram, and in fact, the resolution of the A1 singularity just blow up one P1. But if W is equal to 0, you see that this equation is not. Yes?
You're changing here the dimension, whereas for the E6 singularity you did, right?
Say it again, sorry, I didn't understand.
You're changing here the complex dimension of the singularity, right? So when you start with the C2 mod Z2, it has two complex dimensions. When you add W, and
yes, exactly. So I have a surface, and then I add one extra dimension. So, and this threefold basically is not a product, but is a fibration. Okay, so it's not just a product of this times this, but it's a fibration over this because.
And in the case of E6, it was not the case, right? You took a three-dimensional singularity and you deformed it.
In the case of E6, if you take all this mu to be function of W, then again I have an hypersurface in C4.
Oh, it's C4.
In C4, yes.
Not C3. So
the full space. So, I mean, this is an hypersurface in. So if mu is constant, just a constant, all the mu are constant, then this is an hypersurface in C3, and it's describing the deformation of an E6 singularity. Now I do something different. Instead of considering this with mu constant, I consider this with mu depending on an extra coordinate, W.
I see.
And the dependence on W is a trick, and we'll discuss later how you choose it, etc. But after you have this dependence, then this is an hypersurface in C4. Okay, if you have.
I understand. Okay, thank you. Thank you.
And the conifold, I mean, so here you have the deformed A1 singularity will be just adding some mu here, and now I take mu equal to W squared, and this is the dependence, like in the E6 case. Okay, so the conifold is a family of deformed A1 singularities that at W equals 0 has a surface that has the full singularity. And now what happens if you resolve the conifold? No, resolve the conifold, P1 blows up, okay? But this P1 is exactly the P1 that blows up if you resolve the A1 surface. Okay, so what happens is what is called a simultaneous resolution, which you resolve the full fibration, and if you see what happens at W equals 0, you see that the fiber has been resolved, and the P1. So the P1 of the small resolution of the conifold is the P1 that blows up in the A1 singularity. Okay, so Now, all of this has a very nice gauge-theoretic description that we can understand if we go to the type 2A picture. Now, it's known that if you take type 2A and you put two D6 branes in flat space-time, this is dual to M theory on C2 mod Z2. This gives rise to a 7-dimensional n equals 1 SU2 super Young Mills with a vector multiplet, 7D vector multiplet. This vector multiplet has three real scalars or a complex scalars and a real scalars. Now, what happens if you give a VEV like this to phi? Now, remember that phi controls the transverse deformation of the brane. And if you give a VEV on phi that depends on some word volume coordinate, in this case W, then at different values of W, you have a different deformation. And then what happens is that you tilt the branes. And this means that giving this VEV to this phi corresponds to having deformed the system to two intersecting branes. Now, the intersecting branes, which spectrum do they have? They have an hypermultiplet localized at the intersection. And there is a relative U1 of the branes that plays the role of a flavor symmetry for this 5-dimensional mode sitting in the hypermultiplet. Now, how do we understand what happens in the dual M theory if you switch on this VEV in type 2A? Well, there is a nice spectral equation like this that tells you immediately that if you plug this phi inside here, what you get is exactly the equation of the conv. Okay, because this is the identity 2 times z minus this, and you can immediately compute that you get the equation of the conifold. Okay, so the conifold corresponds to two intersecting branes, and in fact, the conifold has one hypermultiplet charged under a flavor U1. I want just to stress before going on one important thing that turns out to be important later: the fact that in this equation, you see that here you have some polynomial in Z and with coefficient given by function of W, and this function of W depends on the Casimir of phi. Okay. Now, how do we understand this spectrum from the 7D point of view? Now, from the 7D point of view, you have a complex scalars. You give a VEV to the scalar, and what you do, you break the gauge group. In this case, was an SU2. You break to U1, and in this way, you get the flavor symmetry. How do you get then to have a hypermultiplet? Well, this is an old computation. And what you have to do, you have to look for fluctuation of phi of this field modulo gauge transformations, because you want to consider fluctuation that are just gauge transformations. Okay, so to understand which what are the relevant fluctuation, you just see what are the degrees of freedom of phi that you can cancel by, or you can gauge fix to 0 by the choice of delta phi. And this delta phi, we take the linearized gauge transformation that have this form. So this is a generic element of the algebra, and this is the VEV of phi that we on which we want to do to study the deformations. So how do we do this? Well, phi can be parameterized in this way, and I like to parameterize in this way. So it's a 2x2 matrix that is traceless, of course. And here you already read that each element has different charges with respect to the U1, and because the U1 that is preserved is just the Cartan. Okay. How does this linearized gauge transformation look like? You do this commutator, and you get this. So you see that if you consider, for example, the phi plus element, if W is equal to 0, you can cancel it. You can gauge fix it to 0. But you can do this at W equal to 0. Okay. This, in a better way, is saying that phi plus and phi minus, actually, the same, live in the space of polynomial of W modulo the ideal given by W. So basically they are one dimension. Okay, so we have one mode coming from phi plus and one mode from phi minus that are localized at W equal to 0, because everywhere the mode can be gauge fixed to 0. And these actually are the degrees of freedom that sit in one hypermultiplet that is localized at W equals 0, and then it's a 5-dimensional mode. What about this phi 0? This phi 0 cannot be gauge fixed. Any part of gauge no part of phi 0 can be gauge fixed. So this is a 7D mode propagates in 7D. So It's a background field for our 5D theory. Now, having found that we have one hypermultiplet means that we have basically the M2 state, okay, giving rise to the full hypermultiplet. And what is the invariant that counts how many M2 brane states you have on a given curve is the Gopakumar-Vafa invariant. Okay, so by this computation, gauge-theoretic computation, we arrive at a known conclusion that the genus 0 Gopakumar-Vafa invariant of the conifold with degree 1 is equal to 1. And this 1 is exactly the charge of these modes with respect to the preserved U1. We can do something more complicated than the conifold, okay? And, but still remaining in this class of flops, okay, or simple flops. A simple flops means that you are growing up just one P1. And the conifold is obviously you got one P1. There are other examples, and this is the class that we want to study. Okay, so how can we generalize easily? Well, conifold is the A1 family. Okay, family of A1 deformed A1 singularity. We take an A2K minus 1 family, for example. If you take K equal to 2, just to have a working example, we can work out this by taking 4. So we have A3, so an SU4. We can realize by taking 4 D6 branes. And now one would like, for example, to switch on a VEV like this. Okay, it's a block matrix with the 2x2 blocks. Now, what is this? Well, this, if you study what this means at the level of the branes, means bounding 2 branes between each other, bounding other 2 branes, and then tilting the 2 branes. So you have basically these 2 fat branes that are intersecting again. So you expect some hypermultiplet modes at the intersection. You can look what is the preserved symmetry, and it's again a U1, okay, generated by this cartan, and we notice, it will be important in the following, that this cartan is exactly the dual cartan of the simple root alpha 2. Okay, so it's the one that is 1 on the alpha 2, but 0 on the other 2. Well, so we have a U1 preserved symmetry, and you can plug these facts. Yes.
So yeah, so is it the case that you have 4 hypermultiplets in this case? You have 2.
I mean, if you want, I mean, you have 2 hypermultiplets actually. I tell you why now in a moment.
It's 2. You're telling me
2 hypermultiplets, yes. The conifold was 1, and here we have 2. Okay, so if you plug this phi into the spectral equation, the determinant of Z identity minus level of phi, what you get is this equation. This is a known equation. It's called the Ritz pagoda with K equal 2, and in other communities it's known as the A1, A3 singularity. This has one vanishing sphere. If you resolve, you say it is only one vanishing sphere. And in fact, this one vanishing sphere is what? Is exactly this alpha 2. So you go at the origin, this is again a family of A3 singularities. At the origin, you have the full A3 singularity. You expect that you could blow up 3, just in the fiber 3 spheres. But what happens if you blow up this full family, this full threefold, is that only the central node blow up. Okay. So there is a really strong connection between the blow up node and the cartan that generates the preserved symmetry in the 5D theory. Now, how do we compute the modes? In the same way as the conifold, you have to see how many degrees of freedom you can fix, gauge fix. And you see that the gauge fixed phi is of this form. So in this block here, you have 1 degree of freedom, diagonal here, A plus, and 1 here for the B plus. Okay, and you have other modes with the minus. The minus and plus are the charges under the U1. Okay, under exactly the U1 generated by this. And so you see that we have the degrees of freedom of two hypers, A plus A minus and B plus B minus. Okay? So we conclude that the GB invariant genus 0, GB invariant of degree 1 for this threefold is equal to 2, and this was already known before, but we have computed this in this gauge-theoretic method. Now, if you wish, I can show you if you ask me, I can show you the computation of the zero modes. Otherwise, yeah, I go on and explain you this computation.
Hi, Roberto. Can you go back to the previous slide?
Yeah.
Can you explain the asymmetry between A and B? I mean, these are the two hypers, right?
Yes.
Why is there an asymmetry? Is there a simple way to understand that?
But I would say it's just because I write this in this form. Okay. If I go no, here I can no, it depends on how you present this. These are belong to this block belong to. Can you ask me this question at the end of the talk so I have more?
Sure. Yeah.
Okay.
Thanks.
The easy answer is that it's just an apparent mismatch, asymmetry. They are the same thing.
So can I ask a question?
Yeah,
also
sure.
About the previous slide? So yes, so in the drawing of the brains here, I would intuitively put in your phi matrix, I would put W and W and not a 1 on top on the upper diagonal part. So then, of course, it would change the equation. So the equation would be Z4 minus W4, I guess. So what would change in that situation?
So you would, sorry, I didn't follow. So
in the expectation value of phi,
yeah,
your 4x4 matrix, I would put a W instead of 1.
Here.
Yeah, for instance, here, yeah. And so the drawing will be the same. It would also be two intersecting brains like this, right? But the counting would change, or what's happening?
Well, I would say no, because you remember here there is you have the Z, okay?
Mm-hmm.
So if you compute the determinant, you have Z squared minus W squared.
Yes.
And, again,
and then Z squared plus W squared. So this would be Z4 minus W4.
This factorizes a lot. So I would say you get you are not binding the brains, but you get just again other 4 brains, but they are tilted.
So that there would also be 2 hypers, and we could do the same thing.
Would they still be transverse intersecting then, with 2 W's? Question.
Yeah, I guess maybe that's
having 2W here is like having W minus W, W minus W here in the diagonal. So I would say that first of all, the reserved group would be SU2 times SU2. So I mean, it's not an abelian group.
No, sorry, you would have Z to the 4th minus W to the 4th. So this can be factorized into 4 linear terms. Each thing. So it would be like having 4 brains at different angles.
Yeah, you have 2 brains, stack of 2 brains intersecting another stack of 2 brains.
No, not in the case they want, right? Because you would have 4 distinct linear factors on the right.
Okay, yeah, okay. So you say the 4 brains will all have a different angle.
Yeah.
Mm-hmm. Okay, I see.
There would still be a quadruple intersection, but there would be pairwise intersections, and I presume.
I see, yes.
But the different setup.
Okay, but it depends also what you put here, if W or minus W. But yes, you can have different possibility. But with your choice, you're not binding, you're not reducing, let's say, the number of brains. Here, really, you have a recombination of these brains into a brain that wrap a W plus Z square.
And so, just to understand, then in that case, it would not be a simple flop, right? Because then you can.
Yeah.
Okay. Yes. Thank you.
Anytime the preserved group is not U1, you have more than a simple flop.
Mm-hmm. Okay. Thank you.
So what are the number of ND directions between the 2 6-folds?
What are, sorry?
Neumann-Dirichlet boundary conditions. These are D brains, right?
Yeah.
Okay, so how many directions they share and how many they don't?
I don't know if you understand the question. So I can tell you, I can tell you where these 4 branes live, and then.
He wants to know about Dirichlet counting.
Okay. Yes. These are intersections. You have the Dirichlet. You want to know what are the overlapping.
How many ND directions? That's a typical question in OpenString.
The ND is the
you have
overlapping ones, right?
Sorry?
That when you count the NDs, you mean these are the overlapping directions, right? The directions of the intersecting object.
Neumann on one side and Dirichlet on the other.
Okay, so basically you have overlapping. You have a 5D overlapping intersection. Okay, the intersection is 5-dimensional, and you have then 2 directions that are transverse and the other 2 that are transverse. So
then typically, when you have such a situation, you have a U2 gauge to living on the first set of these 6 ways, and the U2 living on the other, and the intersection between them will be 4 hypermultiplets by fundamental. Another way of asking this is how do those 2 hypermultiplets transform under the gauge symmetry that lives on those two sets of these 6 branes?
yeah, remember these 6 branes are not flat. They have a. I mean, they are curved.
So the picture that you draw here is symbolic?
No, it's absolutely symbolic. Yes, they are not flat. They're not plain. These branes.
Well, here they are, right?
Yeah, but I mean, they don't intersect in that simple way, because the intersection, is W equals 0, Z square equals 0. No?
Well, but anyway, I think it's 4 ND directions if you use this vocabulary. Right?
Yeah. It's 4 because you have.
So what's the gauge symmetry living on those 6 branes?
Can't hear.
Those are 6 branes in 7 dimensions. So
yes, they are 7-dimensional. Yes.
And there is a gauge symmetry. There is a vector multiplet.
It's a 7D vector multiplet. Yes.
But what's the gauge group?
The gauge, you have a relative U1 between the two branes. That is the U1 that we are talking about.
Even though there are 4.
No, sorry, I changed the.
Well, it's U1 cross U1.
Okay, they are this way, and these fat branes are given by.
Okay, maybe we should discuss this later. I don't want to stop you. Your plan. Yeah.
Okay.
Maybe we should proceed.
But maybe it's good to make it clear, because this is kind of crucial. And yes, there are 4 branes, but there's only a single U1 in 7D. This is the characteristic of these so-called T branes, right?
Andres, in this case, I don't know if we would say there are 4 branes, because really the brane locus is what I've written, W plus Z square and W minus Z square. So you have 2 branes. If you remember, you can also describe
already the nilpotent piece, even if they were still coincident, would break it. It would be 4 branes, but just in 1.
Right.
Okay.
This is kind of crucial to understand that these are not the usual D branes, they're the so-called T branes, right? There's these bound states, right? So they're already fat, already in the upper picture where you drew 4 parallel branes. You could have grouped them into 2 fat ones already there, even before giving an angle.
And are these hypermultiplets charged under the gauge symmetry that lives on the 6 brane?
They are charged under this relative U1, yes. The U1 generated by the preserved Cartan generator.
So they carry charge 1. Oh, that's the only charge?
Yes, that's the only charge.
I see. Okay. So 2 copies of charge 1.
Yes.
Okay.
Okay, so this can be generalized to the family of A2k minus 1 by taking again these 2k branes and switching on a web this block diagonal in this way. And you find that the other width pagoda, okay, which now it's a family of with the parameterized by this k. You made the zero mode computation, and you see that you get k hypermultiplets, in spite of the fact that this is still a simple float, in the sense that we have only one P1 that is blown up in the resolution, and this one P1 is again related to the this P1 is related, so this spheres is related to the central spheres of this Dinkin diagram that is related to the preserved Cartan, that preserved by this Higgs web.
And again, you say there is one gauge symmetry and k hypermultiplets of charge 1.
Exactly. And again, you have k copies of charge 1, the charge you read here, charge 1 hypermultiplets.
And there is a UK symmetry which acts on them. Is it visible in this picture? You could rotate, since these are identical hypers, you could rotate them.
No, it's not identical, in the sense that here what we see basically are the background vector multiplets. So we see the mass deformation, but I mean, we don't see the symmetry of this.
Okay.
I see that Stefano maybe wants to say something about this.
No, I just want to ask a question. So
okay, I see. I saw your face. Okay. I mean, this. Say that.
Can I ask a question? No?
Yeah.
So here you are selecting the central node. I mean, why do you do that? And I mean, can I also consider other nodes, I guess?
Very good. We are, I mean, I'm going to construct a generic thing, and I tell you why I do. I mean, in this case, I wanted to generate this class of famous threefold. That's basically the reason. For the A family is not much difference actually. Okay, so what I want to okay, so you see we have this structure of the web. It's related to this colored Dinkin diagram. So there is something on it. I mean, something that maybe is already some classification. It is already somewhere. And in fact, it is. First, before going to that, I want to stress one important fact for this phi, that every time that we have, for all the cases that we've seen so far, we have a web that at W equal to 0 is nilpotent. And this is important for why? Because if it is nilpotent, all its Casimir invariants are 0, and then all the coefficient of the deformed AD surface are 0, and you get the full AD singularity you start with. Okay, so this is what we require. So let's consider a generic case then, and then we try to build up these relations. Okay, so we consider a Lie algebra G, a generic Lie algebra G, and a web for an adjoint complex scalar in this Lie algebra, such that its commutant is a subspace of the Cartan subalgebra. Okay, this is important from the geometric point of view, because this is telling us that we have just an isolated singularity. And then we want this phi that depends holomorphically on phi, and that is nilpotent at W equal to 0. Okay, this is basically requiring that in the central fiber should have the full G-type singularity. If you choose a web like that, it's very similar to what happened before. What you have is that the 7D gauge algebra is broken to this commutant that we call H, that will generate U1 to some power. And there will be 5D localized modes at W equals 0 that are charged under these U1s. Okay, so we will get 5D theories n equals 1 with hypers and background vector multiplets. Okay, and for the flop, simple flop, what we require is just to have one U1. Okay, so we have the situation which this phi is commute with H. From now on, I will omit the symbol of the vacuum expectation value for ease of notation. So we have this phi that commute with this abelian subalgebra. Now, saying this abelian subalgebra basically is dictated by which spheres of the AD singularity you want to resolve in the full resolution of the tree. Now, if phi commutes with the abelian subalgebra, means that this phi belongs to what is called a Levi subalgebra by definition. Okay. And now there is a nice group theoretic classifier relation between resolved spheres, so colored linking diagram, and Levi subalgebra. That is telling us actually more. So I just copied a table from the Collingwood book for the A3 algebra. Okay, here you have all possible way to color the nodes. So meaning for us choosing which sphere we want to blow up. And to any of these diagram, there is a related Levi subalgebra. So the algebra subalgebra in which phi should live to generate this kind of resolution. And also there is a related nilpotent orbit that is exactly the orbit where phi at w equals 0 should live. And then you have you can read from this the flavor group. Okay. So after this table is there for any Lie algebra. So if we want to construct some manifold with some properties, we can just come here and proceed. Okay. Now, so what we should do, we should basically choose a flop that we want. Okay, in the previous case, we chose this. We decided to make this flop. So after this table is already telling you what the phi should look like in the central fiber. Okay, and then you have to deform this by a W-dependent piece, such that phi still lives in the Levi subalgebra. Okay, how do you do this without?
Just a question.
Yes.
In the case of if you go back, you have so there are two partitions. One of them is called 2, 1 cube, and it should be 2, 1 square, right?
Where do I put this? Yes.
The second one is called 2, 1 cube.
Oh, no, sorry, I copied.
That's 2, 1 squared.
Yeah.
And I'm just wondering what is the distinction between the two partitions which are called 2, 1 squared.
It's an algebraic distinction. So if you look at what happens at the it's a good question. So let me check that I got it correct.
I suppose there is a Weil reflection that maps one to another, no?
Mm-hmm. I'm hesitating because naively I would say that the structure of the resolved fiber is different, but I understand your point. I should compute the equation and see that maybe the Yau is the same.
Okay. Thank you.
It should be the same, right? Because the determinant depends only on the matrix, and there are just two exchange blocks. Your matrix of the Levi.
The singularity is the same in both cases.
Yeah,
right?
it should be the same.
It's just A1. If we make the spheres really big, then it looks the same.
Yeah. Probably there is a yes.
Sorry, can you repeat the question?
In fact, the appearance here is the same, in the sense that you still have two spheres that are intersecting, because if you collapse this one, you can see. So the question is there actually a difference between these two cases?
Yeah, no, that shouldn't be.
So the equation is the same, and I guess also the resolution.
If this is not crucial for the rest, then maybe we can also discuss this.
Yeah,
afterwards.
it's not crucial.
Okay.
In fact, these are not simple flops, okay, because we are blowing up two spheres. Okay, so if you want to deform in a way that doesn't count also gauge transformation, so you want to go basically in a transverse direction, you go through the slot of the slice intersected with the Levi, okay, in such a way that you still keep this into the Levi subalgebra. So for A3 is very simple in the case that we have seen before. This is the coloring that you want to realize. And then in the Levi subalgebra you read is this one. The phi 0 must be in this orbit, so we'll have this form here, and then you compute the slot of the slice, and you see that intersect with the Levi should have this form. And now what you are left is taking these three parameters and letting them depend holomorphically on W. So any different choices give different Calabi-Yaus. The choice that I've written here gives back the Ritz pagoda that we have seen before. So now we are ready to approach any simple flop. Okay, so I do the example for the E6. And I choose to blow up. So first of all, you have to choose an algebra, then you choose a sphere to blow up. I choose this central sphere, central node, and I will tell you later why it's interesting to do that. And then I read the Levi subalgebra. That is basically given by these three pieces times the dual of this root, the Cartan dual to this root. And then the phi at the origin will be this one. And then I choose a deformation in the slot of the slice, depending on W. So if I do this choice, I have defined completely my Higgs field. And after I have my Higgs field, I can extract the equation because I extract the Casimir of this field also for the E6, we have some spectral-like equations, so you're able to write down the thing. And the way you do is to write this mu in terms of this Casimir of phi that depends on W and plug in the Versal deformation. And we work out an easy method to do this, contrary to previous methods like the very bright but involved method originally introduced by Katz and Morge. And you get this equation. Okay, so this is a threefold, and it's a threefold with a point-like singularity at the origin. By construction, the preserved symmetry of the 5D corresponding 5D theory is the U1 generated by the blown up spheres. Now, what about the zero modes? How do we compute them? Well, now it's very involved, okay, as you can imagine.
Sorry, Roberto, do you mind going back to the previous slide? I'm always slow. So this is not a cone, algebraically, right? There's no C-star action.
This one?
Yeah.
No.
Should I be concerned?
For what?
I don't know.
You'll be a concern if you still want to map this to type 2A, for example, you know?
Okay, so anyway, this geometry is not scale invariant.
Wait, but it's not, isn't there one quasi-homogeneous?
Exactly, it's not even quasi-homogeneous.
Not even quasi.
No, because you have different powers of W, right, in the coefficient.
Yeah.
Okay.
Yeah, I mean, here we are compact defining theory on this tree.
So you mean like maybe it breaks our symmetry theory?
I mean, I'm really concerned about scale invariance, I guess, of the 5D theory that I would expect to be reflected in the transverse geometry. Then we can talk about the R symmetry as well. Yeah, they're related by supersymmetry. Anyway, we can discuss this later.
Okay. Well, anyway, I'm claiming that this is an n=1 5D theory. Okay. Okay. What about the zero mode counting? So as I said, I mean, now it's very involved, the computation, with respect to the one that I showed you for the conifold, because we have a bigger algebra. I show you just the first steps of the algorithm that we worked out to compute this and we implemented into a mathematical file for the reason that you will understand shortly. So now that we have the file that belongs to this Levy subalgebra, we can decompose the joint representation of E6 into representation of the Levy. Okay, you can do for E6. Okay, so you have the 78 is decomposed in this way. Now, what you can immediately see is that each of these representations has a definite charge. So the modes coming from this direction, let's say, the deformation going in that direction, have a charge 2. The modes here have charge 3. The modes coming from here has charge 1. Okay. Moreover, if now you take G, just the G of the gauge transformation just belonging to one of these representation, then the commutator of phi and G also is in that representation. Okay, because phi is in the Levy subalgebra, so this is a representation of the Levy subalgebra. This means that we can study the deformation of phi in each single representation, see if there is some G in that representation that cancel some part of the gauge fixed to 0, some part of that deformation. So you make this computation, we find one mode coming from, or one hyper coming from this representation. So we have one hypermultiplet of charge 3. We have 3 hypermultiplets of charge 2, and we have 6 hypermultiplets of charge 1 under the U1 generated by the preserved capital.
And what is the label G?
G is a genus 0 because these are the genus 0 Gopakumar-Vafa invariant, because these are the M2 states wrapping the blown up P1 for this sphere.
And so there is a similar computation for higher genus?
Yes, but these are 0 for these simple flops.
So
you have this P1 that is you have this P1 that is you look for homology classes of compact surface that are rigid, and you have just this P1.
Okay. Now, will you have let's take the charge 1. You have 6 copies.
Yeah.
So, so if they would couple in Lagrangian, there will be a U6 flavor suit. Do you see such a thing here?
No, again, what we see is that we have just one mass for all of these hypers.
Mm-hmm. You see. Okay.
This is a tricky characteristic of this kind of threefolds.
I see. Okay. And not even the subgroup A2, A1 is not a flavor simple. We should not think of it as a flavor simple.
Sorry, I didn't hear
so you have 3 non-abelian factors and 1 abelian. And
yeah.
I'm just asking about the 3 non-abelian factors.
Yeah, but these are broken by the Higgs, no? So
they are not visible. Okay.
No, the one that is visible is the preserved. So you have an X that lives in this block, say block subalgebra. So you have, the Higgs belongs to this subalgebra and breaks the full E6 to alpha, the U1 generated by this.
Single U1, I see. Okay, thank you.
Roberto, can you say that such independent masses would be broken by a potentially gauged discrete symmetry?
Well, okay, potential that we don't know if they are there.
Well, we see that there are no more masses to be turned on. Is that compatible? Could you have arrived at the same conclusion by imposing that the discrete symmetry that we see be gauged? In order to forbid such terms?
Oh, sorry, I didn't think about this. I don't know if you're referring to something. I don't know if you are saying something in particular.
I couldn't hear it.
No, I don't know if you are referring to something in particular. But maybe
Math terms that are independent for the 6 guys, for instance, right?
yes. Okay.
Would they be forbidden if one imposes as a gauge symmetry the discrete symmetries that we claim we might see?
First of all, I would not claim that there are discrete symmetries here.
The ones that we don't know if they're gauged or ungauged.
Okay. No, but it's not in this case. In this case, if you want to discuss later, but yeah. Okay, so now, I mean, basically, we are able to construct flop of any length. And what is this length? Well, it's a mathematical property of the flop, the blown up Q1. I can just give you the physical definition, because the mathematical one is quite involved. So you can probe these singularities through some D branes, and if you do this for the conifold, you get this quiver. While if you probe this singularity, you get even with one brane, you get some non-abelian nodes. Okay, and this non-abelian nodes encodes some numbers, and the occupation number is the length of. And in group theoretically, what is this L? This L is the dual Coxeter label of the blown up P1. Okay, so that's why I chose to construct a flop blowing up this, because it's a flop of length 3. So it's a high length flop that is. So if you and then you can understand quite easily that if you know the labels for all the algebras, that this L can go just up to 6. For the 6, you need to take the E8 algebra. Now, these flop that we have constructed are non-toric. Okay, are non-toric threefold. And in spite of this, we were able to construct the Higgs branch to compute the Gopakumar-Vafa invariants, okay, through the Fromm method. Now, for all these cases, what you get for the Higgs branches are basically a bunch of hypers charged under the U1, and you get a number of hypers of charge 1, a number of hypers of charge 2, and so on. So all the charges are occupied. Okay, and for all of this, we computed the GV invariants. Okay, so this was the first part of the talk that I want to tell you. And I can say something about the second. I see that the time has gone fast. But before that, is there other questions on?
Yeah, these collection of hypers, are these forming a symplectic singularity?
You mean that the Higgs branch has a singularity?
Yeah. Is it, and beyond that, I mean, what is the overall topology of the space? Is it conical, or does it have any compact directions?
Well, from the FID point of view, what we see is a bunch of free hypers for this simple flop.
So the Higgs branch is just h to some power.
Yeah. Now there is a subtlety that Andres wanted to to emerge maybe, that in fact, I mean, there is something choosing what is the global gauge group 7 dimension. Okay, so here we started from the simply connected, sorry, from the group, the simply connected group mod its centrum, okay, and from there you break the gauge group and you see what's the symmetry. This is just a U1. But if you start from, for example, from the E6 simply connected E6 gauge group, then you could get some discrete factor, and if that factor is gauge, so then you would have some orbifold of the hypers. my feeling is that no, I don't have any because we didn't study the 7D theory or so deeply to claim something about this.
But then it would become conical and singular.
They would become singular, yes. It will be simple orbitals.
If you have a discrete action, then the corresponding orbital would have a conical structure. But I guess that what you're doing is to look at the generic point away from the singularity. Do you have any information which is sensitive to the singularity?
Oh, the Higgs branch, you mean?
Yeah.
Not so far.
Okay.
What kind of information would you look for? Like Coulomb branches at 3 up or things like that? Or
I guess.
Sorry, what did you say, Andres?
I'm asking what kind of information could one look for?
Yeah, the example you gave.
Sorry?
The example you gave was what? I didn't hear you.
I asked like what kind of stuff could be sensitive to the singularity. I mean, other than Coulomb branches popping up, which here we don't expect because it's all rank 0.
Yeah. Okay, this is what I wanted to say.
What else can you look for?
Yeah. So the type of information could be the first of all to figure out whether it's an orbifold or not. That I suspect it's possible to get, but not sure. Whether the group of if it is indeed an orbifold, to identify the group action, and then possibly is it possible to count holomorphic functions, to identify holomorphic functions next to the singularity? So just sticking to geometric information that one can extract about this symplectic singularity.
Mm-hmm.
You would find some inconsistency to find just the hypers?
Yes, so with the hypers, I suppose that what you get here is the dimension of the Higgs branch. So this is very nice. It's a first step. The next level of information would be the symmetry which acts on them. So if there's any way of identifying that there is a, if it's H to the N, then there should be a symmetry SPN. So is there any way to detect such an SPN symmetry? But if not, maybe it's too much to ask. Then possibly identifying the discrete group or holomorphic functions. That's an attempt to answer Andres' question. So it is. I think it's a very important question, and one should figure out what kind of information can be extracted.
So can I follow up? So wouldn't this symmetry only rotate hypers of the same charge among themselves? So already. And if I may ask a follow-up, which was related to what Ami was said, what do you know about the target of this hypermultiplet? Is it really flat? Do you know for sure?
We don't have access to the metric.
Mm-hmm.
Yeah, we're computing.
But you do believe it's smooth?
I didn't hear the last.
But you do believe that it's smooth?
Andres was arguing that there are some.
I mean, if unless there are discrete symmetries which are gauged.
So it's smooth unless it's not.
I mean, it's not clear to me whether this is a non-trivial nonlinear sigma model or
I see.
or just 3 hypers.
Well, there's no gate, there's no vector multiplet in 5D, right? So we don't know, but
I mean, I can still always define a nonlinear sigma model on a curved target, right?
Yes, and then it will not be conical, right? So it will be just a smooth space, no singularities. Andres was saying the emergence of a Coulomb branch, so you don't expect any Coulomb branch to emerge. But please go on.
Yeah, you have to tell me how much I should go.
Oh, I mean, up to you, but
No,
as long as people are here, please tell us more.
I try to skip, and if you see something that you're interested in, you stop me.
But I think it's a very interesting discussion.
Yeah, in fact. Okay, so the other class of threefold that I wanted to discuss is this quasi-homogeneous threefold called compound dual singularities. And then I mean, they are characterized by the fact that they are still deformation or connected deformations of some ED surface, but again, now are quasi-homogeneous. So we exclude basically most of the flops that we discussed before, and of course we require that there is an isolated singularity. So you see, these are classified. So there are infinite families. And there are families of A deformation of A singularity, deformation of B singularity, or B singularity. Here I write up to 6, but of course there's A7 and B8. And their equation is quite simple. They have the equation of the corresponding AD singularity, and the deformation is just 1/3. Okay, so this means that in the versal deformation, only one mu is switched on, and this is equal to W to the n. All the other are identically 0. Okay, and this table is telling you which of the deformation is switched on. Well, now the problem is different. So we want to take this class of manifold. Now we have the equations, and we want to discuss to study the Higgs branch by constructing a phi that is a field vev that is producing that equation. Okay, after we have the field vev, we can compute the number of modes, the symmetry, etc. Okay, so how do we proceed with the conifold, which we already see some subdetails? Well, we have this equation. This is again a A1 singularity deformed by this minus W squared. Now we want a phi that realizes this equation by this. So this means that it must be a phi such that trace phi squared is equal to W squared. This is not unique. You have these two possibilities that are inequivalent. Okay, so this is breaking to U1. It has producing 1 hypers. This breaks to nothing. You have no hypers. Okay, so from the 7D to 5D point of view, right, these are giving a completely different physics. Okay, remember that this is a perturbative. So you have a perturbative 2A dual. And these phi are physical things, are the vev of the whole volume scalars that you can switch on this way or that way, producing different things. So this is a phenomenon that is known as T-brane, okay, which that is simply telling us that the M-theory geometry, in this case, this is not telling us everything about the low energy field. You need something more. Okay, so in a dual type 2A, you have this phi. In M-theory, it's not completely clear how to implement this data. In this setup, since we are describing this threefold by using this phi, we have this data. There is another subset here that has to do with the discrete group, and this is the following. So after you have selected your Levy subalgebra, that can happen that the Levy subalgebra has a maximal subalgebra. Now, the maximal, if phi belongs to maximal subalgebra M instead of L, they gave the same the same continuous preserved group, okay, the same bunch of U1s. So the continuous preserved symmetry is the same. On the other hand, if M belongs to if phi belongs to a subalgebra, it breaks less. Okay, so in fact there is some discrete symmetry. There can be some discrete symmetry. An example is taking the subalgebra I1 to the 4, subalgebra D4, and in this case there is a Z. If phi belongs to I1 to the 4, there is a Z2 subgroup generated by D7. Okay, and the two basically you read by taking the dual Coxeter label of the removed node. Okay. Again, if you compute the modes in this situation, you can take your algebra, starting algebra, and decompose under the maximal subalgebra, and you can read the discrete charge of each of these representations. So if, for example, you find modes here, you find modes that are charged under some Z2. Okay, so now in this case, that is actually a case that is realized in one of these this threefold, that is the simple A2 D4 singularity. You have modes that are charged under a discrete symmetry Z2, and if this discrete symmetry is gauged, then you will have an orbifold as your Higgs branch. Okay, so the idea is to start from the equation and then try to work out this phi. As I said, for the conifold, you have several possibilities, but we interpret the possibility that give less modes, roughly speaking, as T-brane deformation, so something, I mean, some more Higgsing that is hidden, so you don't see at the singularity, but it's there because it's telling, there is the phi that is telling us that is breaking this one. So to realize actually the known result for some of these, I mean, for all these quasi-homogeneous hypersurface, it's easy to compute the dimension of the Higgs branch by different methods. That dimension is realized once phi is taken the smallest one in some sense. So they take the phi compatible with the equation that makes the less breaking, produce the largest number of modes, etc. So we selected this phi for each of these quasi-homogeneous compound threefolds. Of course, I mean, it's not an easy thing to understand what subalgebra M are compatible with the equation. So has some phi that is compatible with the equation. The phi, remember, should be holomorphic. What we used is the homogeneous properties of these manifolds, and in particular, now here it becomes too technical to say in short, but basically, I mean, you have this algebra on which phi belongs to, okay, that is a sum of some simple Lie algebra and some abelian part. Each of these simple algebra has some invariants, okay, and after you specify these invariants, you can specify in some sense the Higgs, okay. So we use the fact that the coefficients that appear in the equation are homogeneous polynomials of this row, and on the other hand, we want that these mu are homogeneous polynomial in W. Remember, they are all 0 except one that is W to the n. Okay, so and the degree of this non-zero mu we call M. So this is telling us all of this what is the form of this row in terms of W. And you see that in principle you could have non-holomorphic row. But since we want a holomorphic phi, the row must be a holomorphic function of W. And this already imposed some constraint on the degree of this partial Casimir. Okay, so again, one can work out. I prepared a more complicated case, but we will just do the simple case now, and then if you wish, I can show you the other. So the example again the same, A1, A3. No, we want to find the phi that A1, A3. This is again the k equals to Ritz Pagod. Okay, so we have this equation. From this equation, we see that we have an A3 singularity deformed by this W squared. So we have that what is switched on here is the 4-degree coefficient, and that is equal to W squared. So means bigger M equal to 2 and bigger M is equal to 4. Okay, so now in this exponent, what is important is the quotient, so we can forget about the great common divisor. And so this M, we can write N and M this way, and this M that appears, where is it, here, is 2. Okay? Now, now we want, so this is 2 here, and if we want that this is holomorphic now, what we need is that this J is degree 1, okay? Because if N and M for this is 1/2, and this must be 2. Okay, so only the partial Casimir of degree 2 or even degree can be different from 0. So we have to look for subalgebras that have these, in which we can switch on this row and set to 0 eventual other or possible other odd degree Casimirs. So the subalgebra that we can work out here are A1 plus A1, A2, or take the full A3. For the A1 plus A1, this is okay, because it has 2 Casimirs of degree 2, the Casimir of A1 and the Casimir of A1. What about A2? A2 has a Casimir of degree 2 and a Casimir of degree 3, okay? But the Casimir of degree 3 must be equal to 0. And then we have only one Casimir of degree 2. But now, since mu2, that now again is a homogeneous function, so it must be proportional to the Casimir, this is equal to 0, this would set to 0 the Casimir, the partial Casimir of degree 2. So in this case, we cannot realize the equation. Okay, for the A3, we could do it, but since we could do for A1 plus A1, we are happy. So it's a small, remember that we are looking for the smallest breaking that we can do. And now, if you choose, you solve this equation basically, okay, and you find that rho 2 is equal to W, and that the other rho 2 here is equal to minus W. So playing in this way, you are able to construct the full phi, and then by the techniques that I showed you before, you compute the number of hypers, the result symmetry, etc. Yes.
So I didn't get the reason why the third Casimir of SU3 is set to 0. Maybe I should say again.
This one or A3?
For A2?
Yes,
A2.
Okay, so we want a subalgebra, okay? The subalgebra has is A2 plus 1 abelian, no? So we have 1 degree 1 that comes from the abelian row. Then we have 1 degree 2 coming from A2 and 1 degree 3. Okay, now since mu3 must be equal to 0.
Why is that?
Sorry. Let me say it a different way. Now, we know that if we take rho to be of degree odd, this will not be holomorphic in W. Okay, because here for this choice we have 1 and 2, so we have J over 2. So we need that J, you can switch on non-zero C only for J that is even.
Okay, thank you.
Okay, so then this means that automatically mu3 will be equal to 0, because if we for this A2, because if you switch on 1 degree 1 and 3, you need for sure this needs. Okay, now you are left with 1 degree 2 Casimir, let's say let's rho 2, rho 3, and rho 1. No? The rho 1 and rho 3 we said must be equal to 0. We have just 1 degree 2. Is rho 2, and we have 2 equations that we have to satisfy, that is mu2 equal to 0 and mu4 equal to W squared. But mu2 equal, since mu2 is a linear in rho 2, is a degree 2 polynomial in this weighted coordinate rho 2, then requiring mu2 equal to 0, set to 0 rho 2. And then mu4 will be also 0. So this shows that it's impossible to find a phi inside A2 plus the abelian that realize this equation.
Okay. Yes.
Okay. Now, here we were happy because we were lucky because we got just a linear row, very simple. So I mean, we know here that the phi restricted to A1 will be of this form. Okay, but if you got, for example, W square or W2, I mean, we have several possibilities, several different phi. Okay, so again, you have to understand what are the choice of phi inside the selected subalgebra that give for you the largest number of zero modes. Okay, and to do this, you can again work, I mean, with homogeneity, and I mean, it's again another tricky step. But I mean, we were able to do this, and we were able then to compute all the data that we can compute about the Higgs branch. Okay. Here I cannot. If you wish, we can discuss later about this. So just show you for an minus 1 E6 what we get. So you see, depending on which n you choose, of course things changes because the exponent of w in the row coordinates change. No, so you have different kinds of possible classes with the n. And for that classes, we can provide what is the resolution pattern. So how many spheres are blown up in the central fiber. Okay, when n is a multiple of 12. 12, remember, is the degree of the Casimir that we switch on in this threefold. If you have a multiple of 12, basically you can take the smallest breaking that you can have, namely having U1 to the 6 as a preserved symmetry. All of these spheres are blown up. The symmetry is U1 to the 6, and you can compute the number of hypers. Okay, since the charge are just the U1 are just the Cartan, these are exactly populate the root elements of the algebra, and the charges you can read there. Now, when you have n that is 6 mod 12, you have this interesting fact that you can you blow up 2 spheres, so you have U1 to the squares, okay, and the phi will live in the maximal subalgebra of this D4, that is A1 to the 4. Okay, I can make this large. Okay, so at the end, what we have is a symmetry that is U1 times U1 times Z2, and we can work out the number of hypers for each type of charges. Okay, charges and number of hypers that you get. The different end, you find the same resolution pattern, but with a D4 instead of A1 to the 4, so you don't have this discrete symmetry. Okay. And then there are the cases in which either you have just a discrete symmetry, this is a 3. Basically, this is because M in this case belongs to the maximal subalgebra of E8. Okay, and then you have this 3 because the Coxeter ladder here is 3, and so on. And you can compute the charges of the hypers under this it's a 3 and the number of them. And for the last, all the other values of n that are not in these ones, you have to take phi, a generic element of the full Lie algebra 6, so you break everything and you have just a bunch of uncharged hypers. And of course, you can do the same for the E7 and for the E8 and write down, I mean, the similar tables that anyway you find in the paper. So let me just conclude, and then we can go to question time. So we have worked out this gauge-theoretic method to approach Calabi-Yau threefolds that are one-parameter families of deformed AD singularity. And we, what I told you is about simple flops that are a very simple Higgs branch, a number of hyper that are at different charges with respect to one single E1 symmetry, or isolated quasi-homogeneous compound wise singularity that has hyper that are charged under a bunch of U1s and some product of ZK discrete symmetries. I just mentioned that these discrete symmetries are exactly the same that you read in the table of the one-form symmetries for type 2B, for four-dimensional type 2B theories coming from type 2B on the same Calabi-Yau. Okay? And the relation between the two can be worked out by basically taking a line operator, going from one to the other. You have to compactify to a circle and then mirror symmetrize. And doing this, you will have some line operator that becomes local operators in the 3D theories, and then you mirror symmetrize, and then you get a zero form symmetry instead of a one. Okay, thank you very much for the attention.
All right, let's thank Roberto. More questions? Okay, no. Everyone is quiet during the question time.
After 1 hour and a half.
What are the dimensions of Higgs branches that you could get?
Okay, the dimension of Higgs branches, okay, here you have 3n minus 3. For these two cases, you have 3n minus 3. For these two cases, you have 3n minus 2. And for these cases, you have, sorry, here you have 3n. 3n. Maybe it's 3n minus 1, 3n minus 2, and 3n minus 3. Maybe this way it's not more. This is because I want a different notation with respect to what my students suggested me.
I see.
But okay, but you can sum all these numbers and compare with the end.
So yeah, and is there a case where you have one-dimensional Higgs branch?
But yeah, I would say the conifold.
And there you would say, what can you say about the structure? Is it possible to figure out whether it's conical or not, for non-compact direction?
Okay, for the conifold, you have a one-dimensional like Higgs branch. So holomorphically, you would say it's just C4, no? Sorry, C2. So nothing. But in fact, this is not true. If you look at the metric, you see that is a tau knot, one center tau knot.
One center, I see. And so there is no Coulomb branch which opens up. Okay. One center tau knot would have 3 non-compact and 1 compact direction. Do you see such a thing?
Say it again.
One center tau knot would have 3 compact and 1, so 3 non-compact directions and 1 compact.
Okay, it depends. In which, I mean, you have an S1 vibration over an R3. If you take an Lie metric, it's this the size of this S1 goes to infinity at the infinity of R3. While, I mean, if you take just a tau knot metric, I agree, and this remains compact until infinity.
Okay, so if you do have a limit where you could take the size of this S1 to infinity. Then the next question would be, so if you focus at the vicinity of this limit, now we can talk about conical.
Yeah, but you see that for this, you need to know the metric. No? Already for the conifold, it was not easy to work out what is the metric. We tried to work out for the k equal to pagoda, but we still didn't succeed to understand what's the metric.
So you're saying you must have the metric. Preferably, you want to bypass, not to deal with figuring out the metric. Possibly look at the holomorphic functions next to this singularity, because you're dealing with algebraic curves. So maybe it's possible to identify good holomorphic functions at the vicinity of the singularity.
Okay, we have more questions for Roberto. Maybe we can thank him one more time. And I will stop the recording.